Hello and welcome. In this video, we deal with the Solow Growth Model diagram. Given exogenous shocks to key parameters, we're going to discover the effect on this model's endogenous parameters. So that is, we see how per worker capital changes, per worker output, and then we discuss how the economy might transition from one steady state to another given those shocks. Usually, with the Solow model, we've calculated the steady state by taking the equations that define the model economy, so like the production function, the law of motion of capital, to find the numerical or analytical solution of the steady state value of capital or output per worker. But with this problem, it's kind of an application or an example of how that you'll find working with the Solow diagram is much easier and intuitive way of thinking about the model and the steady state values. But of course, it's only easier if you fully get how the diagram works. So let's get on to the question. So the question asks, draw a well-labeled graph that illustrates the steady state of the Solow model with population growth. Use the graph to find what happens to steady state capital per worker and income per worker in response to each of the following exogenous changes. So starting off with a change to consumer preferences that increase the savings rate. Okay, so an increase in the savings rate. How do we show that? Well, that's just so that there's a new savings rate that's going to be higher than our initial. So to start off, we should just look at what the economy looks at some kind of initial starting point. So here's a Solow growth model using Wolfram Alpha's demo of some sort. And we have this large green line up here, which is output per person. We have the red line here, which is investment per person. And then we have our blue line here, which is that break-even investment per person. So we start off at some steady state level of capital per person and some steady state level of output per worker. So what happens if we decrease the savings rate? Well, if we increase the savings rate, that's going to shift up the investment line, the S times F of K. So we're going to shift up the investment curve. So we started off with this investment curve, and now we have this investment curve. So remember that investment is just output times the proportion of people's income that they save. So if S, the savings rate, the proportion of people's incomes that they save is higher, then that new investment line is going to be higher for every value of K. Okay, so that's the change, right? We have this shifted up to this. So now let's think about steady state levels of capital. We're at K sub 1 down here. That was the steady state level of capital where investment curve intersects the break-even depreciation, break-even investment line. So we started off at a steady state level of capital at K sub 1, which is where these two curves intersected initially. Now we have a new steady state level of capital per worker at K star sub 2, which is where the break-even investment line right here, which has not changed at all, intersects our new investment line. So given the increase in savings, we can see that capital per worker has gone up. And then lastly, let's think about output per worker, that lowercase y or f of k. So per worker output is just a function of per worker capital, right? This is given the bigger steady state level of per worker capital, then per worker output is going to be increased as well. So we were given this level of output of capital per person, K star sub 1, we are at this level of output per worker. And now jumping up to this level of capital per worker at the steady state, we're going to have this higher level of output per worker. So output per worker has increased. That's pretty much the answer. Here's a nice little summary. Given the higher savings rate, that's going to shift up the investment curve. Doesn't change anything else. Given the shift up in the investment curve, we see that capital per worker in the steady state is going to be increased, and so the steady state value of output per worker is going to increase. The other thing we might ask is about transition dynamics. So remember that if you have a new higher steady state level of per worker capital, if you're at a low level of per worker capital, then you don't just jump up to that new steady state instantaneously. It takes time because it takes time to accumulate the new higher steady state level of capital per worker. Additions to capital, accumulating capital, That's just determined by investment, which is determined by the savings rate, the portion of your income that you save and contribute to capital. Because that's not going to just jump up instantaneously to that new higher steady state, it implies that the transition from this point to this point is going to be quite gradual as per worker capital slowly accumulates, increasing per worker output. So part B asks, a change in weather patterns increases the depreciation rate. Remember, the depreciation rate is like the kind of percentage of your capital stock that's destroyed each new period. And the idea is it takes into account stuff like, I guess, weather patterns that might destroy capital from one period to another. So you might imagine that the depreciation rate is something like 5 or 10% that just kind of destroys or makes capital less useful one period to another. So what's the effect of a increase in the depreciation rate? Well, let's go to our kind of like starting point Solow model again. Here we are. So what happens when we increase depreciation? Well, when we increase depreciation, the break-even depreciation, the break-even investment line, that blue line, increases. So if we started off at some lower point of depreciation over here, as we increase depreciation, the slope of this break-even investment line is going to increase. And we could see that if we started off at a steady state level of capital here, lowercase k star there, when we increase depreciation, we decrease that steady state level of capital per worker. So yeah, let's draw this out. So you can see we had our initial level of depreciation, which was the delta sub 1 there. And then when we increase the depreciation rate up to delta sub 2, we have the new higher sloped break-even investment line. So we shifted from here to this line. At our initial economy, at that initial lower level of depreciation, the steady state level of capital, where break-even investment intersects savings, was this k star sub 1. Given the new higher break-even investment line, given the new higher depreciation, we have this lower level of steady state capital. What does that imply to output per worker? Well, output per worker right here, it's a y star or f of k star. That's just a function of capital per worker. So if the steady state level of capital is decreased, then the steady state level of output per worker has also decreased. So we've decreased from f of k star 1 here to f of k star 2 here. So we were at this level of output per worker, and now we're at this level of output per worker. And then once again, just a note on transition dynamics, the move from here to here isn't instantaneous because capital isn't destroyed instantaneously. It's going to slowly be destroyed given the higher depreciation rate. To summarize, given the higher depreciation rate, this higher delta, we're going to increase the slope with the break-even investment line. That's going to decrease the steady state per worker capital. And then that's going to decrease the steady state per worker output. Okay, let's move on. Part C asks, better birth control methods reduce the population growth rate. So let's go back to that kind of initial starting point Solow growth model. So we have our model here. What happens if we decrease the labor force growth rate? So given that we decrease the labor force growth rate, that break-even investment line, you can see it's just a function of delta and n. N is the growth rate of the population. So if n decreases, then the slope of that line is going to decrease. So if we started off over here with this lower level of per worker capital, when we decrease the population growth rate, then per worker output per person is increasing. And per worker capital is increasing. So looking at that on the model, if we started off at this break-even investment line, this higher one here, and our savings, our investment curve is unchanged. So we start off at a steady state level of k star sub 1 here. Given the reduction in population growth rate, we shift down that break-even investment line, implying a new steady state level of capital, k star sub 2. So per worker capital has gone up, And if per worker capital has gone up, then that implies that per worker output has gone up. So output per person has gone up as well. The Y star has gone up. I should also kind of note on the intuition of this, usually if you think that population is going up, that the economy is getting better, right? A faster growing economy, we often think is associated, a faster growing population, we often think is associated with a faster growing economy. So how does that work in the Solow model? Well, remember the Solow model is focused on per worker, like per capita levels. So per worker capital and then per capita output. So if you have high population growth, or you have any population growth at all, for each new worker that enters the labor force, the economy has to produce them some amount of capital. They have to take the capital stock and divide it among a larger number of people, because if the population is going up, there's more people, and so each person in that labor force and the economy needs access to some of that capital in order to have some output per person, some additional output per person. So in a lot of ways, population growth basically works the same as depreciation, in that if you have higher population growth, you need to grow that, you need to give a bigger portion of the capital stock to those new additions to the labor force. So by reducing the labor force growth rate, you don't have to give, you don't have to give as much of your investment to those new workers. And so each individual worker can have a larger portion of the capital stock. And so the steady state level of capital goes up, and therefore output per person goes up in this model. So to summarize again, given the increase in population growth, N has gone up. N going up decreases the slope of that break-even investment line. And that implies that, per worker capital, the intersection of investment and the break-even investment line increases, which then implies that output per worker increases in the steady state. So part D asks, a one-time permanent improvement in technology increases the amount of output that can be produced from any given amount of capital and labor. So what does that imply? They're basically saying this, you had that production function, that per worker production function, f of k. So now we're just saying that, it's improved in some way. So that there was some initial level of output per worker. We're going to call this production function f sub 1k of k. And now there's a new one that's even more productive. We're going to call f sub 2 of k. So our production function has improved. The technology is better. So how do we show that in the Solow diagram model? This is the best way that I could think to show it. So we start off over on this left-hand side diagram. You have you have an investment curve here, S times F sub 1 of K. You have your break-even investment line, delta plus N times K, break-even investment, and you have a production function per worker, right? So we start off over here at this level of capital per worker. Then comes along this improvement in technology. So to show that, I just kind of made light blue the old lines that are shifting now. So our initial output per worker, F sub 1 of K, is going to shift up to the new better technology production function. And then the investment line, savings times the production function. The investment line is just savings rate times that production function, so that's going to shift up proportionally as well. So where before you were down here, now we have this higher level, right? So before you had output per worker of this F sub 1 K star, given that initial lower level of output per worker, given that initial lower level of capital per worker, we now both have a higher intersection, right? The depreciation, the break-even investment line, intersects our investment line at this higher level. So we have this higher level of output per worker, but then we also have a higher production function. And so you kind of have the double effect, right? Where before, when we shifted from a steady state level of capital to another, we were basically moving along our production function. Now, we're not only going to this new level of capital per worker, we're also jumping up to a new production function. So to summarize, what's the effect of an improvement in the production function? Well, that's to shift upward in our production function line. So this is output per worker, and then this is investment, so that shifts up. And then that's going to produce for us a higher steady state level of capital per worker. So that's the shift here from K star 1 to K star 2. And that also implies a significant, like a much bigger jump in output per worker. So output per worker was this F sub 1 K star, and now it's up to this F sub 2 K star. And so summarizing everything in one graph, we have something that looks like this. So given an improvement in technology, that means our production function is getting better. That's going to increase the investment curve and the production curve. And so that implies a higher steady state level of capital per worker, and that implies a higher steady state level of output per worker. Great, that's it. Hopefully that was helpful. Let me know if you have any questions, and thanks and have a good day. Bye.